All right. So we are covering the Gram-Schmidt process, which is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. Okay, but let's just review. What did we do last time? What we did last time was orthogonal projections. Oh yeah, and it was basically an extension of a single projection, and it's projecting not only on a single point onto another vector, it's onto a subspace. And you basically do this process where, well, this is the general one if you don't have an orthonormal basis. But, sorry, not this theorem, but this theorem. So this is how you find the closest point, given any orthogonal basis. And you should think about why it needs to be that this fails if U is not an orthogonal basis. Because the operation of projection is necessarily producing a point that is whose difference is orthogonal. Okay, all right. Starting to get it. All right. I need to drink a bunch of water. Give me a second. All right. All right, let's get reading. So the Gram-Schmidt process is a simple algorithm for producing an orthogonal or orthonormal basis for any non-zero subspace of Rn. Okay, so if you have a single vector, then it's already an orthogonal. Yeah, sometimes it's nice to just think about, okay, you read something like this and you try to invent it yourself. So if we have a basis that's one-dimensional, meaning a single vector, it's by default orthogonal because there's only one thing. It's not orthonormal, so the way to probably produce the an orthonormal basis in the case where there's a single vector is to just divide by the norm. All right, but now let's look at the example. Let W equal the span of x1 and x2. Construct an orthogonal basis. Okay, so what do we want? We want an orthogonal basis for W, so the span cannot change. So that's one thing, right? The span cannot change. Okay, so let's look at this. This is a good picture. So we have x1 and x2. And our goal is to find along with x1 and x2, the projection P of x2 onto. Oh, interesting. Oh, interesting, dude. That's actually kind of cool. The component of x2 orthogonal to x1. The component of x2 orthogonal to x1 is going to be. Oh, wow. Okay, that's very interesting. Which is in W because it's a linear combination of x1 and x2, right? Because what is P? P is going to be x2.x1 over x1.x1 times x1. Right, this is what P is. Then V1, V2. So V1 we took to be right. So you get to pick arbitrarily one of them. That's like kind of the seed in a way. So you do this thing, you show that they're not dependent. So V Bro, I want to take a nap so bad. The next example fully illustrates the Gram-Schmidt process. Okay, now we have three vectors. They're clearly linearly independent because we got a pivot in each of these ones. So it's thus a basis for some subspace. Now we want to find an orthogonal basis. All right, so we just let our first vector that we are going to be orthogonal to be x1. Let v2 be the vector produced by subtracting x2 from its projection onto the subspace. Oh, dude, Gram-Schmidt orthonormal. This is a great algorithm. Let v2 be the vector produced by subtracting x2, or from x2, its projection onto the subspace W1. Okay. So we're progressively building out the subspace. That's really what's happening. Let V3 be the vector produced by subtracting x3 from x3 its projection onto the subspace W2. Okay. So Graham-Schmidt, you basically take, so step one, take V1. V1 equal to x1. Step two, project x2, and then the let span of V1 equal W1. Project x2 onto W1 and let it be equal to proj of onto W1 of x2. Now add to our basis x2 minus proj onto W1 of x2. And then you just keep doing that. Exactly. I got to think about the 2D case, actually, or the 3D case. So here's V1, here's V2 prime. V2 prime is just the scaled one, right? And then we have, so we're going to project right, so this is going to be a linear combination of, so this projection is going to be in, oh, yeah, so it's forced to be orthogonal. We don't know what V3 is, right? We don't know, so this is how we find something orthogonal. And it's iterative, so we just keep adding orthogonal vectors. That's a very beautiful theorem, actually. Hey, what's up, Chirag? Bro, I'm not going to help you. You got to grind yourself. No one can help you in the world. You got to grind. That's what it's all about, dude. This is beautiful. Okay, orthonormal basis. So now you just divide, right? Once you have your orthogonal basis, you can just, so an orthonormal basis is constructed easily from an orthogonal basis. Simply normalize all the VK. Yeah, exactly. This is easier than normalizing each VK as soon as it is found because it avoids unnecessary writing of square roots. Yeah, that makes sense. So you just do it at the end. So you just divide 1 by the norm times V1. All right, cool. All right, QR factorization. If an M by N matrix A has linearly independent columns, then applying the Graham-Schmidt process with normalizations to x1 from of x1 to xn amounts to factoring A, as described in the next theorem. This factorization is widely used in computer algorithms for various computations, such as solving equations and finding eigenvalues. Oh. All right, QR factorization. If A is an M by N matrix with linearly independent columns, then A can be factored into A equals QR, where Q is M by N and R whose columns form an orthonormal basis for call of A. Wait, what? Q is an m by n matrix. So what is call A? Call A is all linear combinations of the column space. So if that's a basis, then I'm pretty sure then m has to be greater than n, right? Because if m is less than n, yes. So wait, hold on. All right, we can do this. The n columns of Q would be dependent. Okay, yeah, that's what I thought. Okay. Okay, so theorem 12. QR factorization. Given a m by n where n calls are independent, then a can be factored into q times r, where q is m by n and with orthonormal columns that are a basis of A. Basis of for call of A. And R is n by n upper triangular invertible. Upper triangular invertible and positive diagonals. All right, here's the proof. The columns of A form a basis x1 to xn for call of A. Construct an orthonormal basis u1 to un for w equal to call A with the property 1. With property 1, this basis is constructed by Graham-Schmidt or some other means. Let Q equal U1 to UN. For K equal to 1 to N, XK is in span of, yeah, obviously, which is equal to the span of U1 to UK. So there are constants R1K to RKK such that Okay, so then we let Q. So okay, first, Graham Schmidt on calls of A. Calls of A. Equals U1 to UN. Okay? Now for any... Oh, now for each of xk, since xk is an element of the span of x1 to xk, which is equal to the span of u1 to uk, then there are, okay, then there's a then there are constants r1k to rkk such that the sum of r1i ui is equal to xk. Note that for I greater than k, r r1k I is equal to 0. Okay, so rk equals r1k to rkk to 0. And q times rk is equal to xk. Then we let r equal to r1 to rn. Then a equal to x1 to xn is equal to u1 to un times oh.